Let me start with the idea of what this will be about, this session. First, I want to introduce SIMD. I expect many of you know what it is. Some of you may have heard it, but don't know the details. I hope I can get you all on one page here. Then I'm going to go to the data parallel types, which implements SIMD from the programming language side. And then I will show some extensions to that. And then finally we come to something that goes into how this is relevant for GNU radio. I will do a very simple example and then show how this is important in the context of merging blocks and how merging blocks and SIMD somehow go together in a way. One of the goals for this talk is that this is for you. So if you want to follow along and you get lost at some point, please speak up, unless you want to get lost anyway. But let's make this as interactive as is useful for you. If we don't make it through all the material, then so be it. But it's more important that I don't lose most of the people here, then it's not useful. Okay, so why are we talking about SIMD? SIMD is short for single instruction, multiple data. What this means is that you have multiple operations, so a plus is an operation, in one instruction. In other words, that means you do the same work in less time. Or as a picture, you have all these additions, one after another in time. Now we block them together. And you see you have higher throughput, lower latency by doing that. So this is a feature of our processors. But there's another feature that is very similar. It's called instruction level parallelism. What this means is you execute multiple instructions in one CPU cycle. Or in other words, you execute the same work in even less time. So as I put in that picture, the block with those 4 additions, I put another one at the same time. So even more throughput. And the idea of the SIMD type in the language is to express data parallelism, so a bit more abstract than the actual SIMD instructions. And that data parallelism then can be translated into whatever the system, your CPU, can do. And that is both SIMD and instruction parallelism. I showed this on the slide. Actually, the stdx that I use there for the type is a shorthand for std experimental. That's because the type that we're currently using is not in the C++ standard. It's another ISO document. It's a so-called TS, technical specification, which is kind of a better version of what goes into the standard. So we're expecting that C++ 26 will have a SIMD type, or somehow named that way. For now, it's std experimental SIMD. It is shipping in GCC since a few years, and there is my library SIMD that we are also using that abstracts that dependency on GCC away so that you can use it portably with other compilers and other standard libraries as well. All right. So to continue motivation here, I wanted to show an example of how we can reach peak flop. Flop is abbreviation for floating point operations, typically measured per second or cycle. In this case, I want to look at this per clock cycle of the CPU. What's behind that example here is something we typically do. We give our compiler sequential scalar code. And then the compiler can't do anything useful with it. It cannot create any SIMD code out of it. It cannot invent parallelism where there is none. If you have this chain, dependency chain, there is no parallelism to extract from for the compiler. And so this is a completely made up example and not useful at all. But it is good slideware to explain the problem. And it's not that far away from probably a Taylor series expansion, right? You often have these multiply add sequences, and you have the result of that going into the next multiply add sequence. A more realistic example, of course, would use different coefficients for every iteration. But to make that simple, and also to make Google Benchmark happy because it wants to execute the loop as long as it decides is necessary to measure properly, yeah, I just reuse the same constants there. And it makes it much easier to actually reach peak flop, because reaching peak flop in serious real code is so much harder. But it's an interesting exercise. So what this benchmark does, it just creates one float object, initializes it to 0, and then the fake modify is some optimization barrier, basically telling the compiler, please forget that you know that it is a 0. You still know it's a float, but you don't know the value anymore, because if it knew the value, then it could compute all the steps, right? And then the Google benchmark decides how many iterations it does. And then in the end, you're saying, well, compiler, I'm using that value, right? Because otherwise, the compiler would say, you're not using it, it's dead store, I'm going to eliminate everything that comes before. And so your benchmark would be really fast. So I need that fake read. I could do something else and use it, but then I would measure that in the benchmark. So I'm faking everything here. Those are just tricks with the compiler. Now if I compile that and run it, you see I measure 0.25 floating point operations per clock cycle, even with O3 and basically all optimizations on. And then if I turn on this march equals native flag on this machine, I get a speed of a factor of 2 already. I'll come to that in a bit. So compile flags matter. We noticed that. But now let's just change the type. I'm going from float to a SIMD float, and note this is actually using std_SIMD, so that's the prototype for C++26. You will not be able to replicate exactly that code for now. But the basic idea here is you go from float to a SIMD float, and now you have multiple zeros. Again, not useful. But you could initialize this with different data. You have your array of data, you take that whole chunk as initialization, and then you do the same process. I mean, a Taylor series, all the coefficients are always the same. It's just the input data that is different, all your measurements that are different, right? And so that is a realistic thing you would do. You would just take a bigger chunk and then calculate this on a lot of inputs at the same time. So what this type here is, you're saying, give me a default SIMD float, which the implementation chooses for you, knowing what your target is. And you ask it, what's that size? And it says, in this case, because it's compiling for an AVX 512 system, I can put 16 values in there. And then me, as a person who knows how my CPU works, I say 16 times 8, please. I want more. And so 16 times 8 is 128. So if this sounds like a GPU to you, yeah. So we're doing 128 floats basically at the same time, in a hand-wavy way. And going through that benchmark loop. And if I compile that and run it, you see we're getting 8 flops without the march flag and 64 flops per cycle with march native. So a speed of 256 compared to the naive loop. So what happened here is this 0.8 times 8, it increased our instruction level parallelism by a factor of 8. Because the SIMD width, which is the SIMD float size, is 16. This is also already a good speed up, but there's so much more in the processor. And this is a tuning factor, something that you, in many cases, have to try. Because there is an architectural thing that you could theoretically derive this, but the more complex your code becomes, the harder it is to see how much instruction level parallelism is still available for you to use. And if you go too high with that number, then things could become inefficient again. So it's not always very straightforward how to do this in a performance portable fashion, but at least there's an interesting tuning knob that is easy to reach. And it is easier to reach in C++26 than it is with the current TS, but it is also possible there. So the reason that first implementation was slow is because there was just no parallelism. It is just one long dependency chain. We need a mic over there. I think that one's not working. Where's the blue one?
So just to back up a second, so this you're getting this because there's, like in this particular processor, you have 2 ports, 2 FMA ports?
Yes.
Okay, good. Just to
so
clarify the obvious, not so obvious, because it depends on the machine.
Yes.
Okay, but it can issue 2 per clock or whatever.
Yes, that's totally dependent on the machine. So there are Intel processors with AVX 512. Some of them have 1 FMA port, some of them have 2 FMA ports. That makes a difference in terms of ILP. One of them wants to have a 4 there, the other one prefers to have an 8. The 8 should work for both of them. It's just that the speed up you get is different for those different processors.
So how, is there any tooling to look inside to see, like for Intel compilers, you get like this nice tune thing where you can look inside and see, okay, this pipeline is mostly running empty. Is there something similar in the GCC LLVM world?
So I will show something in a bit where you can get an idea of parts of the code. It's basically you need to look at smaller regions of your code where you have the loops and then try to understand what is my instructions per clock cycle, right? That is the thing, the number you need to look at. And then you always have to know what your CPU can do, because without the knowledge of the theoretical reachable number, that number is kind of useless, right? Of course you want to get it up, but if you don't know what you could reach, it's so much harder. Yeah, I will show something, how I typically go about it, at least. Right, and the other thing is this arch flag. If you don't tell your compiler where you're going to run your code, the compiler has to assume, well, that's the architecture. That architecture evolved over time. I cannot make use of the new things because you might want to be compatible to the old things. And especially with x86, there's a huge evolution. 2006 basically is when the 64-bit architecture came out, and you had SSE2 in that. So that's the baseline for 64-bit. And if you just compile without telling the compiler what your machine will be, that's what you're going to get. That's 2006. And that is pretty low on that graph. There's a factor of 2 that we were able to get just with a bad code already by putting the arch flag there. And that happens on GCC. It doesn't happen on Clang because it contracts the multiply and the add into a fused multiply add instruction. Clang doesn't do that by default. You have to pass another compiler flag, fp contract equals, and so on. That's because they interpret the standard differently on whether that is something they may do or may not do. And I have been trying to resolve that issue also in the committee, but so far we were like 50-50. Need to write another paper. And so really important here, if you have a very capable machine that you're going to run on, you really, really want to turn on these arch flags to get the AVX 512 instructions. They are so much more efficient. even if you don't want to make use of the full width of the register and just want to use half of it, you still want the instruction coding of AVX 512. And just recently, the Zen 5 architecture was announced. Don't know if you've seen that. Zen 5 has a 2x speed up compared to Zen 4 on AVX 512. So by now, Intel is walking back from AVX 512. They don't want to do it anymore. And AMD, like, yeah, we got the speed. So this is super important. And I'm not sure yet whether Zen 5 has another 2x up that red line. I did not understand it yet. Yeah.
Maybe just to inject a question or a hint for the people who are going to package GNU Radio. This is very critical, whether you say you do a generic installation that runs anywhere, and then as you said, like it will be stuck with the performance of 2006. Or you say like you branch out, that you compile for different architectures and fall back to the slowest one that the computer supports. Or I throw in like another suggestion that we should maybe discuss about just-in-time compilation, where you have like a base installation that has okay performance, but then that the SIMD is recompiled on the fly.
I mean, the first thing is I would paint the first thing differently. You can either package software or you don't, right? If you package software, you need to support the platform that your user has. So that's not an option. I can't package something that needs a Zen 5 now because no user would have it, right? The other
Yes
question
and no.
that I ask is whether is there some infrastructure to build multi-microarch binaries so that I don't have to do in-time compilation.
Yes.
Yeah.
So the glibc, the dynamic loader, has infrastructure for that. Below the lib directory, there is another directory structure for different ABI versions. And that's basically SSE, SSE4, AVX2, AVX 512, and so they have it not as fine-grained as the march flags are, but at least the vector width. And so what you could do is you put everything of your application into a lib, a dynamic lib, and then you have a very small executable that is just linked to that. And then the dynamic linker will go through that directory structure and try the first one that your system you're running on supports. If it doesn't exist, it goes to next and so forth until it gives up and doesn't find anything in there and then takes the normal lib directory, which is the case for almost all of it. But if you ever look at this with strace, you see that it looks at all these strange directories when it's trying to find the lib. And that's where you can, at this point, as far as I understand, package things in a way that can already make use of this.
I have one question. Do you have any like speculation why Intel may have dropped it and then AMD picked it up?
Maybe we do that speculation afterwards.
Okay, great. Thank you.
I do, yes. So, actually, I want to say that I think we write and use code as impossible as that first example all the time. A very prominent example is all of C math. You have these functions, they have this library boundary to the C library, you give it one value, you get one value back. And so what the compiler does, because this is so bad, is the compiler sees, I know that function. I'm just going to replace that with a built-in. And that built-in, I can optimize everything out of this. Because I know how it's supposed to behave. And I completely ignore that the library has an implementation. I mean, I can use it if I don't want to do some optimizations. But so what the compiler can actually do here is if you put on fast math and O3 in GCC, it will pick up a different implementation. It doesn't take the cosine float. There is a cosine that takes SSE vectors, that takes AVX vectors, and so on. So that's the auto-vectorization of those CMath functions that the compiler can do just because it knows those functions. But your functions will never become part of the compiler. So as long as we write these interfaces, we have that problem. So the function is often the inhibition for making use of SIMD and instruction level parallelism. So here's an alternative. If you say cosine of a SIMD of float, and the SIMD of float allows any number of elements, 1, 2, 3, 4, 5, that is a host of functions, and now the caller can use whatever it needs and gets the parallelism out of it. And to be a bit more general, we want a concept that takes a T or a SIMD-T. Maybe you've seen that concept come up before. There was a GNU radio process 1 T or SIMD-T. Yeah. Okay, now I'm going to do some overview of what the SIMD type is and how it works. And I will try to do most of this not via slides, but Compiler Explorer, some life hacking. I hope you can all read this. You don't have to understand it at this point. I'll walk you through this. Okay, for now, you can ignore everything above here. All we're looking at is the part down here. We have a function that returns something, and we just print that something using cout. Okay, simple enough. And what it does, it creates a float, returns it, and so we see down here it prints 1.1. Simple enough. Now I'm going to do a simple replacement of the type, and then it recompiles the whole thing. And now we're returning a different type, right? We're returning a SIMD, and the cout now has to have an operator that does it. And basically this is just printing that SIMD, so it's iterating over it. So we're passing a SIMD here with a V and print it via this with the loop. It just subscripts into the V, gives us all the elements. And so we print down here a vector of 4 elements. Okay, that's 4 elements. Now if we look up here, I actually told the compiler I'm going to compile for Skylake architecture. Now Skylake has AVX2 available. AVX2 has vectors with 8 floats. Why am I not getting 8 floats? The reason is that the committee wanted to be conservative for the TS. And I said SIMD should default to whatever the most common denominator of that target is. So a SIMD of float will be SSE for x86 64, and it's actually going to be a scalar for 32-bit x86 because that is like the common denominator. So if you want to have this scaling with whatever you're compiling for, you're asking for a native SIMD. So I changed this to a native SIMD of float, and now we have 8 results. But what actually happened here, so we initialized a SIMD that has 8 elements from just one value. I call this the broadcast constructor because you have this one value and it's being broadcast into all the elements of the float. You can also default construct it. Default construction leads to 0 initialization. So I'm expecting 8 zeros there. Oh. Come on, Compiler Explorer. Yeah. Okay, so you can just initialize it. Like if you do int parentheses, you get a 0, right? So you can do the same thing here. We can also not initialize it and get all the problems that leads to, so if you don't initialize a float, you don't know what you're going to get. We're likely to get zeros here as well because typically everything is somehow initialized first. The stack is zeroed before the first use, so you would have to put data on the stack to see something. But even then, compilers nowadays try to zero over the stack sometimes and make sure it doesn't leak too much. C++26 will even have that part in the language to ensure that you get something sensible and not leak any data. So these are the 3 simple ways we can initialize this. There's a next very important one, because typically you have data as an array of floats already. Now, how do you get that array of floats into your SIMD? So I have an array of floats right here. It's a C array. And I'm going to say this. So I'm giving it a pointer, right? Data as a C array is all decays into a pointer. So there's a load constructor of the SIMD, and that, yeah, you are right. There's a load constructor, and that takes a pointer and a load store flag. Sadly, in the TS, no one wanted to have default for the flag, so you always have to say what you want. You have to say, is it aligned? Is the pointer aligned to an element, or is the pointer aligned to a whole vector? So alignment means basically a multiple of the address. Right, and I'm saying that even here, I'm saying align as 64. So that means the pointer data, the pointer value, the number, is a multiple of 64. Now, if you know your x86 instructions, this one up here says vector move aligned packed single precision. Aligned. I said element aligned, not vector aligned. How did you know? Actually, the compiler is smart enough to know by itself. It says align as 64. The compiler knows that data is aligned. So just saying element aligned doesn't hurt. It's safe. It's not going to crash. Because if we say it's vector aligned, and then I put a +1 here, it's obviously not aligned, right? I took a line pointer and I... Come on. Nah. That's always the danger with Compiler Explorer. It's, whoa, it's... See, the compiler is too smart. It actually omitted an unaligned instruction because I said it's aligned and the compiler said no. Apparently it's too smart for me. Okay, let's try something else. So yeah, okay. The point I wanted to make, let's not try this here because it takes too long to compile. The point I wanted to make is if you say vector aligned, you're making a promise that if it breaks, leads to a seg fault. And these are often puzzling when you're then going through with GDB and say, where is my outer bounds? My pointer is totally valid. And yeah, it is. It's just not. You have to look at the address and then look at it in hex and see that it has enough 0 bits in the end. And then you know why it crashed. So just typically put element aligned there unless there's a very good reason. You saw from benchmarking, element aligned will give you, at least on x86, best performance anyway. Whether it says move U APS or move A APS, those two instructions have mostly the same speed on the machine. There is an actual difference whether the pointer is actually aligned or not, because you get cache line splits or not. And these cache line splits lead to twice the number of cycles required for loads and stores. Okay. There's another constructor some people might expect, right? Let's make it a 4 SIMD. We can do this with std array, but we can't do this here. Yeah, sorry for error messages, but they are. I would like to make them better, but the language doesn't give me all the tools. So this does not compile. And the reason why this does not compile is because it does not scale. Right? If you write this code, you don't know whether you're going to get 4 elements. It could be 1. It could be something else. And here for native, it's even worse, 1, 4, 8, 16. So what would be the right number of values to put here, and how to interpret if something is missing or if there are too many? So instead of being able to do this, we can give it a function. And so if you don't know what a lambda is, that was introduced in C++11. I'm introducing the lambda with the capture syntax. Where is it failing? No, it's not. With the capture syntax, I'm not capturing anything here. And then I say I take one function parameter, I take an int. The int basically tells me the index position in the SIMD object. And then I'm going to turn that into a float and return that, and that will initialize the according element with that index. And so I'm getting a vector 0, 1, 2, 3, 4, 5, 6, 7. This is actually a very useful vector in SIMD programming. Sometimes you need some offsets in memory, for example, and that's exactly what you typically have then. Now here's a curious and important thing, and I will show this in another example as well. If we try to return a double from this function, it should not compile anymore. So SIMD has, in comparison to the other built-in types that we have, a bit more safety built in terms of conversions. Conversions just need to be value preserving. So if you go from int to float, that is not value preserving because float only has 24 bits in the mantissa. But if you go from int to double, that is value preserving. That works. You can typically not go from any floating point to integer because there are so many values in a floating point that you cannot represent in an integer. That doesn't work. So you cannot go from double to float, but you can go from float to double. And the same is true if we try to initialize with a broadcast. If I just put .1 here, this will not compile because I'm giving it a double. And I'm just not going to wait for this. I need to put an F here and make it a floating point literal, and then this compiles. This is typically more important when you do any kind of calculation, like times 0.5. This is something that sounds useful. But again, that does not compile because what needs to happen here is you have the left-hand side and right-hand side of a binary operator, and the first thing you want to do is both of them should become the same type. So the compiler checks, can I convert the left-hand side to the right-hand side? A SIMD float to a double? No, does not make sense. Can I convert a double to a SIMD float? And yeah, you could, but do you really want to convert down from a double to a float without the user actually calling that out? So what happens if you say float times double is that the float becomes a double. So what do you expect, the SIMD float times a double to become a SIMD double? This is bad because of performance. We suddenly need twice as many registers. We lose a lot of performance in SIMD programming if we do that. So this does not compile. And again, you just have to add an F here to make it a floating point literal, and then this compiles. All right, all the arithmetic is probably the interesting part, but look at this, the compiler knows what I'm doing. It is not emitting a multiplication. It just loads one value from LC1. Where is LC1? LC1. There's LC1. So this is our, yeah, in floating point, it's a 0.5. So you get all the constant propagation that's happening at compile time with the SIMD types. And where it didn't work, and I found it, I made sure that it somehow works, either by bug reports to the GCC optimizer or by workarounds in the library. So if you find any constant propagation ever that you think should work, write a bug report. It's a performance bug, missed optimization. Okay, and Also, importantly, let's just take the sign of this thing. So here's a slight curiosity. If you have a float, you cannot normally, at least, write sine of x, because that would be the c function. In C++, there's only a std sine function. So you would have to say std sine of x, but then std sine of x does not compile with the SIMD because that's in the std experimental namespace. This will change again with C++ 26 when it's become proper part of the C++ standard. But for now, if you want to fully qualify this, you have to say std x sine. But there is a sine implementation that, so there is an optimized implementation for sine and cosine. I did not come around to do all the other ones, so there's a lot of work left. If you ever want to do an exponential, talk to me first because I have most of the work done. Yes?
So by default there with just sine of x, you're getting the double result, and then it's, why is it not complaining? Isn't sine of x going to return double?
No, that would be the C function.
Okay,
So this is overloaded on all signs.
Okay.
So it takes a sine of float and returns a sine of float.
Okay,
SIMD
great.
float and returns a SIMD float.
Okay, thank you.
Just like the std sign. If you do a std sign of float, you get a float. But if you say just without qualification of a float, then it would convert it to double, yeah. At least in theory it should, but there might be strange things implemented in some cases. Okay. Let me go back to the slides and see what I forgot. So this is important information. So there is this size function as a static const expr function. Means you can call it directly on the type. You don't have to have an object. And it's a const expression. So you can use this in template parameters. The size is something that's chosen by the implementation, and it should always depend on the compiler flags you pass. And for most targets, this relation holds, that there is a certain size of the register, and then you have to look at the size of the element type, and that determines how many elements you get. So there will be twice as many single precision floating points in a SIMD than double precision. Similar for integers, but this is not something you should rely on without at least a static assert, because there are special architectures out there, like for example Intel's Sandy Bridge, which introduced AVX just for floating points, but not for integers. I mean, the register is there, but the instructions are missing. Okay, so you saw the SIMD type. I did not mention yet that it has this second template parameter. I will just come to this. This first template parameter is allows all vectorizable types, which in the TS are all arithmetic types except bool. So this also includes the character types. Means you can vectorize strings right away, and wchars and whatever. We don't have bool there because we have a special type for this. It's called a SIMD mask. It's basically supposed to behave like a bool, but in contrast to bool, we need to have many different mask types. There are different ways of storing this in a processor. Some of them are bit masks, some of them are full width vector registers, and of course we have all the different SIMD widths. And then there's this ABI tag parameter. And this one is hoping to help you with a lot of headaches. Because consider you would compile one file with march equals something old and the other one something new. And then you have a function with the same name, with the same type, and the type, if it has the same name, the linker says, well, yeah, I can link this. And then you run it, and you get garbage or segfault or whatever. But by having this ABI tag, I can tell it, yeah, this is actually a different name. Even though in the source code you wrote the same name, underneath it's actually different. And then when you link it, the linker says, nah, those two are not compatible. And then you go back and figure out how can I talk between those translation units. And there is an API tag in the TS that's called fixed size, which you can use for communicating between different API, between different translation units, and also potentially over the wire. I'm not going to get into that. So we've seen this. So I talked about loads. We also have the stores as the opposite to that, to go from a SIMD into a given pointer. Again, you can say element or vector aligned. All the arithmetics, I showed this before. Yeah, let's do the compares. All of the operations that are shown, they happen element-wise. If I do in plus, it's per element in the SIMDs. And I do the same thing for compares. So that means if I compare x less than y, I get multiple answers. And you cannot say if multiple answers to this, otherwise this, right? It's many. So what you can do instead is you compute the result for all of them and then say where this is true, do the assignment. So that's branch-free programming. It's conditional assignment. It's kind of like the question mark operator in a sense. Sadly, I can still not overload question mark, but I have a paper on this. And the other important thing you can do, whenever you have a collection of things, you can do a reduction. You just have to say how you want to reduce it. And so for Booleans, you want to be able to say are all of them true, any of them, or none of them true. Back to that where function, you can think of it basically as if per element is true, then per element do the assignment. And this one supports not only plain assignment, but all the compound assignments. So plus equals, and so on. Permutations are not part of the TS, but I copied the paper that is progressing towards C++26 into the VirSIMD implementation, which is a third-party dependency of GNU Radio, so you have that available. And there's a SIMD permute function in there. And what you do here is you have a similar problem as with the initializer list. You cannot say, well, these are the 4 indices on how you should do the permutation, because you want to be able to scale to different vector width. And so instead of giving a fixed number of indices, you'll give it a function where, given an index, you compute the other index of where to go. And then this function in this case just swaps all the neighbors. And important here is, in order to produce efficient code, we need in the instruction this 177. It needs to be coded into the assembly, so it needs to be a constant expression. This lambda will be at compile time completely computed, and then the compiler figures out, yeah, I have to encode 177 for that specific permutation here. Reductions, I mentioned them for masks. There are 3 more. Population count, so how many are true. Then find first and find last bit that is set. Basically, what's the index of the first true, what's the index of the last true. And then there are also reductions for SIMD, which basically work like the std reduce we already have in the library, that where you can pass any range. You can consider SIMD being that range here. And so if you call reduce on an X, it sums up all the values. You can give it a different function for the reduction function. But we can also mask it, so we can say reduce where X is positive, only those values you should sum up. The functions for reducing to the minimum value and maximum value have a different name. That's mostly for technical reasons. This is going to change in 26. And that is sometimes quite useful. So if you if you do searching, that happens that you're looking, for example, for the smallest thing in a big array, and then you do all the minimum reductions, and then at some point you decide, okay, here it is, and then you wanted to return the index of that thing. How do you return the index of a value you just found? Well, you take that value, you compare it again with the SIMD you just looked at. So you do this comparison equals. That will give you a mask. Now you ask for the first one with that index, that where it's true. You get that index, and that is your position. Typically, the implementation of such a reduction is a tree reduction. And in terms of performance, keep in mind that this is not the full speed up, because when you're doing the tree reduction, it gets basically smaller and smaller in terms of the parallelization that you do. So if you have something big that you want to reduce, don't take a SIMD, reduce, SIMD, reduce, SIMD, reduce, and then sum them all up. That would be like wasting so much. Take those SIMDs plus the next, until you have only one SIMD left. So accumulate in a SIMD and then do the std reduce on the SIMD in the end. That's going to be so much faster. We've talked about reflection a bit before. I want to do something here with SIMD as well. So if you work just with floats and doubles, SIMD in the TS works fine for you because you can just replace it. But most of us have more structured data. And you do it as well. You have complex, at least, real imaginary. And at this point, it's not there. But very simple things, like you can define an aggregate like the point here, and then say SIMDice that thing. It's a meta function that produces a new type, which is kind of equivalent to a structure that has now a SIMD float of these three. Sadly, they are not called X, Y, and Z anymore because I don't know those names, and I especially cannot recreate those names. This will hopefully happen soon in standard C++, but not yet. So for now, what happens is you get kind of a tuple that has a SIMD interface that you can use. And this is already happening in GNU Radio under the hood. So SIMDice is used in there if you ever have a sample type that is an aggregate like this, and you are asking for SIMDs, you're going to get these SIMDiced meta transformed types.
Excuse me, so in the actual implementation, is the fourth field or whatever padded out to zeros in these cases? Or, I mean, I'm basically packing the struct into the...
So you mean the second struct?
Yeah, well, it's...
Yeah, you don't need any padding because each...
Sorry, this is the array of vectors versus vector array conversation, okay.
Yeah, so this is actually in between. So if you would have an array of points, that would be your array of structures. And now if you create these point V's and make an array of that, it's actually an array of vectorized structures. So you did not do a complete transformation to a structure of array.
Okay.
Okay, there's documentation. So the TS stuff is directly on CPP reference. Yeah.
For the last slide still, is this also useful if there's types that have different native SIMD sizes? So if you have a double and a float, then...
Yes, so that works. It uses some heuristic of what you probably wanted in terms of width. And it will have to use the same number of elements because otherwise that doesn't make sense. And so one of them has to either use double number of registers or 4 times or whatever. But yeah, so you can have that mixed. You can have even have it nested. So if there's another structure inside, it will just recurse and transform all of these. Another thing to mention, and this is documented, it's basically documented here, how this SIMDice works. If you here give it a template, type name T point, and then say T X Y Z, then I'm going to do something different. And when you instantiate that with a float and then give it to my SIMDice, point float, I'm going to make that a point SIMD float. Right? So you will have your names of the members still, with some checking that it's doing the same thing as it would otherwise do. Like if you have a T, X, Y, Z, and then a float something, that wouldn't work anymore. So I'm guarding against that. Okay, that's documented just all in the README, all the extensions on top of the TS. Time. Okay, let's do some signal processing. You all know signal processing, so we can go fast here, right? This is very similar to a process bulk function. We're getting in a span, we want to put out through a span, and I'm just implementing a gain here. So from now on, this precondition that the size is equal, we're going to assume that. And there's this simple implementation using a for loop, seen it all the time. And we can also do this using a standard algorithm. It's longer, but we're going to see how this is helpful in the end if you write it like this. So here we're basically saying go over this range, right into this range which starts there, and this is how you should transform each element. So we're calling it with a value out of this, and the return value goes into here. Okay, so how can we use SIMD in this example? We need to look for loops, because that's where typically all the data parallelism is. What the loop says is take this one value, do something, write it back, increment I, and only if you've done that, go to the next one. And this is kind of problematic, both to the compiler and to the CPU, because he said, I'm going to read something here, and then write, and then read from a pointer. How does the compiler know that this next read is not what you've just written? It doesn't. So in C, there is a keyword called restrict, which mostly doesn't work as far as I am experienced. It does not exist in C++. There are extensions, __ restrict, and it still does not work. So the compiler assumes, yeah, there could be aliasing. So if you then actually tell a compiler, please vectorize such a loop, the first thing is, of course, it checks whether this range is actually 0. If it's 0, it goes out. The next thing it checks is, if it's trying to vectorize it, well, those two pointers I got here, are they far enough apart that I can take a chunk, store it back, and not override what I'm going to read next? So it does some pointer computation and then says, OK, I can take the fast path. And the interesting part here is that we encoded this into our loop, because we said, do this first. And when you're done, do the next step, because that's what we're saying with those semicolons, with those for loops. But actually, as the programmer, we knew about the parallelism all the way. It was clear to us that this is just data, and we just have to work on each of those samples. We don't care in what order. We just have to do it. So the simple way to do that is by saying, go over them and do it. We didn't meant to say, do it one after the other. We meant to say, just do it on all of them. And so we lost that information about the data parallelism. And it's right there. And we want to just do that by saying, OK, instead of a float, put a SIMD float there. It still has the problem that at this point, your chunking size, well, the compiler will see at compile time a fixed chunking size. So it has to assume there could be, again, load store issues. But on a higher level, at least for the developer, if you look at it and you just said native SIMD float, the native SIMD could be 1,024 values. If you go into a GPU, possibly even more. So at least on an abstract level, you encoded the complete data parallelism there, because you didn't constrain it to a certain width. So looking at this, where's our float here? It's just hidden in those temporaries. Let me make an L value out of this. I call it sample. And now just change the type from a float to a SIMD float. So this is what I recommend if you want to go from an existing code base to using SIMD. Just look for your data types, replace them with the corresponding SIMD type, and then go from there. So at this point, it's not correct. Because what we're doing here, we're looking at a single value. So this is a broadcast constructor. We're copying in all the elements that doesn't make sense. And even worse, down here, this does not compile, because now we want to, say, put a SIMD into a single float. That does not. You need a reduction to do that, and we didn't say how. So we need loads and stores here. So that's the load constructor. We're giving it now the pointer to the first element where to start reading from. We always have to spell out element aligned. And then when we're done, we need to copy it out into the out pointer, again, element aligned. So this compiles. Do you see what's missing? Yeah. You're one step too far, actually. Yes. We have a plus I still. So we still go sample by sample, and we compute every sample multiple times now. This is not very helpful. So the next thing here is how we go about the increments. We now go by the number of elements in the SIMD float. And as you correctly mentioned, there's undefined behavior in here. The bounce check is not right. Right? We don't know at this point that the size is a multiple of the SIMD size. So if you consider the size would be 7 and the SIMD size would be 4, that's an obvious out of bounds. So we have to change this condition. For example, by saying, okay, if you go another SIMD size further, that's got to be less equal, and so on. Okay, so we're running out of slide space. This is no fun. And actually, okay, let's do something here. This is recommended practice from my experience, that you don't go all the time with saying SIMD float, and or more explicitly stdx SIMD float. Just put a float v somewhere. And then if you ever do mixed precision, this is the place you want to define all of them. Then you say float v is my workhorse. And then I'm going to do a double v that has the same number of elements as the float v. And then mixed precision becomes easy. And then if at some point you decide, well, maybe I should try the other way around, that the double v defines the size, then this is your only place where you change that. And then all over the place it still compiles. You can do the mixed precision stuff. Okay, so we have that shortened. That helps us a lot. And I took out the I equals 0 out of the for loop so that we have information after the for loop what is still to be done. And so we have to write another for loop to finish with the rest that we failed to put into a SIMD because there was not enough there. So we call that an epilogue in SIMD programming. Am I asking you to, from now on, just write 2 loops instead of 1? There are more possibilities. You can also do this with a recursion and then go from SIMD to half SIMD and further half and so on. Many possible approaches of how to do that epilogue. And if you decide, well, another one is better, and you go over all your codes and change all your epilogues, you're going to be so not happy and curse me. I have good news. I don't like this. So I implemented all of this in GNU Radio for you. Right? Just implement process 1, and you're good. So the thing we just saw, all this stuff here, you just have to tell me this. And the rest GNU Radio does for you. It does the epilogue. It does all the handling. Typically, it doesn't need to do an epilogue because you tell it in the port that you want a power of 2 values. So it knows I'm starting from a page-aligned buffer pointer, and I'm going in chunks of 1024. Never gonna need an epilogue, right? And so you don't have to do that, and the core knows it. It has more information than the block has. And that is why the process 1 is so interesting, because now You're saying, I can take a float, I can take any SIMD float, all I have to do is multiply with this gain, and however this is chunked over the memory, I don't care. GNU Radio, do this.
Thank you.
Yeah. Yeah, I didn't plan on implementing SIMD there. I was doing something else, and I saw, hey, this is such a good fit. I just have to do this. I can't stop myself. You don't have to do this as a template like this. You can also overload on a float and a SIMD float. The thing is, here you still have to allow different ABI tags, because in case it wants to do an epilogue, it might want to do smaller SIMDs. And then you need to be able to accept different SIMD widths. I would recommend don't do this unless the code is really very different. And it can be different if you want to have lots of if statements in here, which are not going to work here, where you need to do branchless implementation using the where function. But you could also use context per if in such an implementation. There's another approach. So if you have to implement a process bulk, then start from this std transform implementation. And you can always, there's always this implicit execution policy of going sequentially over this. Spell it out. And then there's this minor tweak. You change the execution policy to ver execution SIMD. So that's part of the SIMD library. And what it does is exactly what I just showed. It does this for loop, chunking the SIMDs, doing the epilogue. And then this is why you have to put an auto here, because it will give you SIMDs of different sizes. So you can do that as well. And I implemented for each transform, transform reduce, and a few others. If you need more, write a feature request. I wanted to, how much time do I get for live hacking? Okay. I think this is interesting enough that we should look at a few options here. Because you always also wanted to see how I do some of the analysis performance-wise. So this is me and my Vim, and I have a plugin that you can find on GitHub. There's in the exercise link that is on Indico, there's also a link to this Vim Compiler Explorer plugin that I'm using here, but also other ways of inspecting this are documented there. So this is the transform that I just showed on the slide. And if I compile this, I'm going to just quickly go over this first part. Basically here is where this gain, which is a single float, is broadcast into the YMM1 register, which is 8 values of floating point. And then after checking whether it can do so, it goes into this loop. So it's a multiply of 8 floating points, loading from the in pointer, and then the result, the YMM0, is stored back. That's the move double quad unaligned, stored back to the out pointer. And then it increments this A register by 32, which is just the step, right, for the next, which is added to those offsets here, the in pointer, out pointer, plus this offset. And then it compares, am I done? And otherwise loops. So this is the loop that comes out of this first for loop doing this. And now there's LLVM MCA. So up here is the call that I just did. I called LLVM MCA on the code that I just highlighted here. And so what this does, it starts with, okay, I simulated 100 iterations of what you just gave me. And it said, I found I had to execute 500 instructions and I needed 139 cycles to do so. there were 700 micro-ops. So if you're not familiar with that, every instruction is actually not executed. It's turned into micro-ops, and those are executed. We ignore the micro-ops for now, but we see micro-ops per cycle is 5. That sounds good. And instructions per cycle is 3.6, also a good high number. Whether it's actually good, I don't know, it's high. And so there's more information here. You can try to dive deep. So it tells you about all the instructions, what are the micro-ops, the latency. Latency here is high because it's loading from memory. If it's actually coming from L1, it's not going to be that high. This MCA is not going to know where it's at. But if it's L1, this is just full throughput. You can do 2 loads per cycle of SIMD registers on x86. And only 1 store. So we actually store limited here. Because we can also do 2 multiplies per cycle. It's the store that's going to limit us. If you go further down, there's more analysis. It tells us on which execution ports these instructions are likely to be scheduled. And here we get a timeline analysis of when the instruction is decoded and then put on the execution unit and when it retires and so on. And you see the dependency when it does the iterations, how you have this dependency on A, and there's further analysis down here on the average wait times based on that timeline view, and it tells you how many executions, average time spent, and so on waiting and so on. Okay, now this is hard to interpret, if you ask me, but if you stare at it long enough, it's useful.
On this particular machine, does the hardware prefetcher have enough buffering to fetch from like DRAM all the way through, or from L2 to 3?
Yeah, this is actually not doing enough work. So if it's way out of L1, L2, L3, performance is going to drop down a lot. I'm going to show a benchmark in a bit with a very similar one where you see that. But let's do something here in terms of ILP. We saw the effect of ILP before. So my execution policy here, the SIMD execution policy, has policy modifiers. And so I'm going to say, I modify the behavior by unroll this by 4. Loop unrolling by 4. Okay, so what do you expect? This is what happens. So this is our main loop now. We see 4 multiplies and 4 stores back into out, just to compare and jump. And up here we have the modification of the variable. And it's actually not doing an in pointer plus anymore, but it's now moving the in pointer and the out pointer. The compiler decided that might be better. I don't know why. So we can try to analyze that. We see way more instructions, total cycles. IPC went down. It's hard to interpret. In the end, it's faster. So you also need to benchmark this. Kind of the reason why IPC went down is because notice that we had this loop overhead. We had the addition of the A register, the compare, the jump, and only 2 of those instructions of the whole loop were doing the work. And now the ratio is different. And now we're actually stalling on the store throughput. This is limiting it. And so since that is limiting our performance and we have way less other work to do, the instructions per cycle is going down, while the whole performance is going up. So don't just look at that number and get it up. You need to understand what's going on. And benchmark, benchmark, benchmark. So again, you can try to analyze this down here in the timeline view and how it's waiting. We're not going to dive deeper. So there are more modifiers that you can play with. I just, in the last days, implemented assume matching size, which was fun. It basically says, assume that the size of the range you're going over is matching the SIMD size in terms of multiples. So this got nicely short because the epilogue is gone. And you get safety. You get safety here. So the first thing it does, checks for 0. So if it's 0 size, it just directly returns. Then the next thing, so this is an AND. It checks whether it's actually true, your assumption you just gave me. And if it's not true, it's jumping into this cold region down here and it's calling UD2. If you ever saw UD2, it does a trap. So if you're, it's kind of saying, get me into the debugger, please. Otherwise, it's, I think, a sick bus or so. So you have some safety here. And to, there is...
I have a question.
Yeah.
With contracts, if I can guarantee the calling function that this condition is met, will the second if vanish?
What do you mean in the second if?
Well, the epilogue, the check. When I know,
Yeah.
when I give by contract, I say by this function designed to meet this criteria.
Yeah. So C++ contracts, as proposed for the language, will likely not do that, because there is a lot of pushback to the idea of contracts leading to assumptions. So the idea is that contracts only add safety, but do not add optimization opportunities for the compiler. So my answer is likely no, even though I think it would be interesting if it's a yes.
Static asserts, would they?
No, static asserts not, but an actual assert, yes.
No, if I would put, if in my code I have a static assert before that by compile time ensures that this case will not happen.
You cannot assert that at compile time. Unless it's a std array.
Yeah, for example.
Yeah, for a std array, but then that check would also be gone. The compiler would see that this is 0.
Okay.
I actually, so okay. Let me go back to this fun one here. Just have to mention my heroes. If you see this a function up there, it takes an iterator, turns it into a address, so a pointer, and then says, assume that pointer is aligned. Now the compiler thinks all the pointers are aligned to 32. Now what that means, if the begin and end are both aligned to 32, yeah, it must be a multiple of the SIMD size. Right? So I tried whether that optimizes correctly, and it did not. So I wrote a bug report yesterday to GCC, and like an hour later, yeah, assigned to me. That should be simple. I will fix this. I love it when I write missed optimization. So Richard Biener, one of my heroes at GCC, always implementing my missed optimizations. But anyway, the one thing you can see here now, I added this assume aligned, and you do not see it on the mul.ps because that does not change, but you see it on the store. Now it's a move APS, so aligned store instead of an unaligned store. So the compiler can see this here by just, if it knows the pointers are aligned, it does the right thing. Okay. But I wanted to show another feature that I implemented. So this is a span. What if we create a subspan of 17 elements? And then we say, assume matching size. Compiling. Oh, does not compile. So this is something I implemented in VerSimD. I've showed this before in GSI in our C++ user group. A check of the preconditions that can happen at compile time if the optimizer sees it. So you have a bit of control over how the preconditions are checked. Again, this is documented in the README of VerSimD. And so here the optimizer can actually see it has 17 elements in the subspan. You just told me it's a multiple of 8. I can check this in the optimizer, not really at compile time. So the front end doesn't see it, but the optimizer sees it, and it throws a compile time error, and it points us right here. that this is going wrong. And you can soften this, and then it compiles into a warning. It's actually still an error. Yeah, whatever. That's live hacking. Okay. So the idea is that if it doesn't see it, so we're going back to this. We're still saying assume matching size, and we saw before that. Why is it not? No matching function. Okay, let's just go back to this. And we saw this before, that it implemented this this check and the jump down to the UD2. You have more control about what happens there. So if we say check preconditions 1, then it's actually just deleting that branch. So it now says built-in unreachable instead of built-in trap on that point. So you're saying really assume this. Don't even check. So we get shorter core code, but less safety. So the default of VirSimD is this 3 where you get a trap. You can go further. So this is errors at compile time and information at runtime. So at runtime, it will actually print at this point in your program, this is wrong with those values, abort. So you have more debug functionality. And I'm trying to implement this for all places where there are preconditions, basically undefined behavior. And so you have a better way of debugging this. My time's up. Okay, just quickly to the benchmark. This is very simple. We're just going over a sequence, modifying in place with a plus. We have these, so we have unseek in the standard library, which says kind of vectorize this as a loop. And then I have SIMD on the other hand. Okay, benchmark this. Very simple implementation, standard C++ 02. That's our performance. Now, if I put the SIMD execution policy, that's much better. Now, if I take the standard for loop and put an 03 there, please vectorize this for me. Okay, that's nice. For unseek, it also gets. Why is unseek slower than the normal for loop? This is just embarrassing. And then with SIMD type execution policy, it's still a bit faster. So the 03 did something more than just vectorize. It did something that also helped the SIMD execution policy. It's probably doing unrolling. But I can say unroll by myself. And you're seeing this line up here. That's the theoretical maximum store throughput of that machine. So we're reaching the maximum. But then in the end here, it breaks down because the range just gets so big that we're not in L1, L2, L3. And so that starts to dominate the performance, and then they're all the same. But in general, in GNU radio settings, you would be in small buffers and wouldn't have those huge buffers. But yeah, this can be limiting. Just to mention here, I think the important part here is in comparison to loop vectorization. With data parallel types, you have the control, you have the composition. We were able to say, well, this is how we want to go over the memory, and this is what we actually want to do with the memory. And this composition of these two, now I can pick and choose how I want to go over the memory while not changing what I'm doing. I can change what I do without changing, and that is very, very helpful. Okay, now a bit more GNU radio and merge blocks and how I actually came to adding SIMD to the whole thing. We have an Amdahl's law problem. So if we optimize everything out of the blocks, at some point you're going to see speed up for the blocks, but not for the whole system. In other words, what's said here, the overall speed up of using SIMD, the whole flow graph may still be frustratingly slow. You don't get that much speed up because we had great improvements of throughput and latency per block, but because over time, we have to invoke the block, process the samples, invoke the next block, process the samples. What happens here is the block writes to memory, scheduling happens, you have the buffer management, you have to avoid over and underruns with the circular buffer. Then the next block reads the input from memory, you probably have some cache memory latencies, and then the whole thing happens all over again. So we still have overhead. And to get rid of that, you have to write your whole application as one loop, right? Then you could just, doesn't have to go back and forth all the time. I have a better alternative. Let's just use the results from A immediately when with B and skip this in between. But this requires the connection at compile time. But it does not require us to implement a new block that merges the functionality. Right? If you have a block and you just need a gain on one of the inputs, copy the whole thing and add a new parameter just to put a gain there. Copy and paste programming maintenance, this is a nightmare. But for performance, yeah, you might want to consider this otherwise because you have this buffer in between. It costs you extra in performance. But if you can just at compile time say, merge a gain onto that input port, and it comes at no cost at all in terms of performance, because typically that gain is lost in all the other work. It's instruction level parallelism. It just consumed. It's for free to add a gain wherever you need it. And so you can write blocks without gain on every port. You can then later add them. So how this works is, instead of this timeline, we want to get rid of this and invoke A, process the sample, and then B, with a good chance of those computations actually getting interleaved. And at least for now, a mergeable block implements process one instead of process block. And here, one, again, for the SIMD case, means one object, not necessarily one sample. So it can be a SIMD object with multiple samples. So a better picture looks like we're going from this, where we have the invocation calling this work function, which does the loop over the process one functions, and then going to the B work loop over the process one functions, into a new type, the A plus B type, which now has a work function, which does a loop over this. And so it calls the process one function, and that's the return value of that goes directly into the input of the other one. And if those functions are inlined, this is merged into a single process one function at compile time. And you get all the optimization you could ever get. This is writing the whole thing as one loop. You can't do this any better. Right? The merged block is this efficient loop implementation that you would otherwise do if you don't have. Sorry, what?
Until you run out of L1.
Not necessarily, no.
I mean, because all of a sudden you start getting stalls. I know that you're running on monstrously big Intel hardware where you don't even, you never care. You've got like many, many megabytes of cache.
But,
right?
but no, what's actually happening here is this work function loops over the input. And now instead of doing little work per one sample or per SIMD of samples, you do a lot of work. So you keep your
iCache, not data cache.
Yeah, okay, iCache.
iCache.
Yes.
iCache is like is on the order of L1 iCache is on the order of like 16K.
But in the end, the merged one should even be less total code size than if you have the individual ones.
Yeah, this is the one where I wonder. I mean, I don't doubt the total, but the question is, there's experiments to be done on relatively small cache sizes that just see what's the right answer. Do we have to chunk? Totally love that we can merge, but then I wonder, the tuning gets to be crazy because I might have to start merging or not merging depending on the characteristics of my cache, which doesn't look automatable right now.
Maybe I can explain a bit, because in the work function, each one of them also checks whether the validity of the required input samples and output samples is correct, and which is not done in the process one. So by merging it, this check is combined from the block A and B, and you execute one, so that reduces already the code size because you have only one check is a superset required for the overall input and output. And then the code that you actually inline, because you removed checks that are superfluous, becomes smaller.
Imagine you have a whole modulator, a whole transmitter, right? And you take the I'm merging it all.
No, I fully agree. I mean, like if you put the whole program, eventually it will not fit into L1. It will be chunked up and then has to be loaded.
Yeah, that's my point. And on some very popular, really high, shockingly great performance,
but
superscalar out of order, but small cache.
I think there's kind of a misunderstanding here what the problem is. I think the cache in any case would not fit the whole problem that you compile, whether it's multiple blocks or not. It is many places in your binary, and you will have to load into instruction cache in any case. So the main question is whether all these process one will be inlined into one thing, and that will not happen. The compiler will say, well, that's going to get too big. I'm going to make function calls out of this. So these process one boundaries, they will be still there. And that's a decision the compiler will do because it says, well, this is just getting too big. That doesn't make sense.
The compiler's not going to know the cache configuration, even by the march flag.
It does. It has all this information about all the CPUs, what is the cache size. So if you run GCC, it runs another program called CC1+.
Yep.
Try to look that in your process list. It has flags on L1, L2 size, and so on.
Okay.
And that is derived, especially when you run with march native. You will basically have a way of inspecting your system that way, because CC1+ will have that as arguments. So it is input to the compiler how big the caches are.
All right.
And there are more tuning parameters also with regard to how inlining works and when to inline and not to, because it's all heuristics, and the compiler can never do the right thing. So you can also tune that.
Okay, thanks. I'll check on the ARM.
Yeah.
Maybe they just don't. Maybe the GCC doesn't have all the data, possibly.
Possibly, but I think ARM people are submitting that, so it should have.
But there's no some ARM processors that are quite popular. There's no microarchitecture manual for them.
I just wanted to clarify. So right now, complex values don't work yet. So that was the point V example, right?
Yes. So complex is still on my list to find time for. Yeah.
Okay. And the other thing is, so in a lot of cases, you might have a resampling situation, and also in that case, you can't merge, right?
Yeah. So if you have any sample rate difference, you would have to do a process bulk, and then at this point, merging doesn't work.
Okay. So
I can envision ways of still merging in some cases, but at this point, it's not there.
All right, thanks.
Okay. Just a quick picture here again, how this merging improves things. So first, without SIMD, with SIMD, we're going in bigger chunks. Then we have per block this bandwidth increase, but this is where Amdahl's law bites. So we want to get rid of this buffer in between, and this happens when we do the merging. And it's hard to go any faster between two given buffers. All right, I need to finish this. So currently vectorizable types, all the arithmetic types other than bool, that's part of TS, depends on C++ 17. There's lots of work going on targeting C++ 26 and beyond. So we kicked out long double because it's useless for SIMD. You get a size 1 SIMD, and it's just a headache to implement and nothing else. So thank you for letting me drop that. And there's a paper it is already design approved. It's just waiting to become part of the standard wording to add complex to the vectorizable types. So you would have a SIMD of complex. Not a complex of SIMD. So SIMD of complex means that your SIMD stores real, imaginary, real, imaginary. So when you do a load from an array of complex, it's a direct copy. Whereas a complex of SIMD would mean you have a complex where you store a SIMD of reals and a SIMD of imaginaries. And you see you would have to permute on loads and stores. Both have their pros and cons in terms of performance characteristics. But at this point, we're only targeting SIMD complex. And then we're looking at more like enums, std byte, in any other user-defined numeric types could become vectorizable types. So we do have prototypes, we do have a paper on this, but it's unlikely to make C++ 26. We want way more interoperability, direct conversion to from array and span, and any contiguous range where it makes sense. The masks are pretty much like a bit set, so that conversion should come. We want an initializer list for SIMD, even though I showed you the problems with it, so it's a bit tricky. And we're considering making SIMD and SIMD mask read-only ranges. There was no ranges back in C++ 17, so I couldn't even think about it. But when we do that, we have like std format just falling out because it formats a range now. And you can do things like vector SIMD T, just flatten that with a range adapter, and you have like a range of T. And that can make some of the problems very simple. Gather and scatter. Like, you can write this with an int right there, int indexes. You know what that means. But if I turn that into SIMD int indexes, should it not also compile? I mean, the meaning is clear. So this is gather and scatter is sometimes hard to use. The performance of this is bad because gather and scatter performance on every machine is just like bad. So maybe we don't want to make it that easy, but yeah, so this we'll look at. So summary here, I think SIMD is for you because you care about latency and throughput. You want to express data parallelism, not think too much about SIMD, like when you focus on instructions registers. And the types enable you the separation of what do you do serially, what do you synchronously parallel, and where you want to do threads. I believe that the API of SIMD designs guides you to do a scalable design in terms of scaling with the vector width. And there are now in VerSIMD high-level algorithms to make it much simpler to access ranges of scalars. And we have the high-level specialized abstractions with control where loop vectorization otherwise fails you. And as I mentioned at the beginning, you got an API and ABI for being able to pass many floats as one over library boundaries. And now you can start thinking about things like Volk, right? Libraries of that sense to become more accessible and more general. And if it becomes part of C++, this is a vocabulary type that the whole world can speak. And things become so much better to interoperate. Okay, just one more thing I have to show. And that is exercises. If you want to use SIMD, you should get your hands dirty. So there's a link on here. There's a link, should be a link down there on the Indico, yes. If you go there, this is where you land. So this is tutorial material that I created way back, so it doesn't use the benchmark facilities that are used in GNU Radio. It's built on top of Google Benchmark, but that is not an important point here because all the framework should just work for you. So if you want to set this up and play with this, basically just copy this to get started. You should have GCC anyway. You want to, for those exercises, probably install a new VerSIMD on its own. And here's your starting point for the benchmark exercises. And then this walks you through how to do benchmarking, how to do it wrong, how to interpret it, how to get the right numbers. So you need those optimization barriers for micro benchmarking, how to get that right. A bit about inspecting, like using Compiler Explorer, other ways of looking at the assembly and interpreting that. Here's a link to the Compiler Explorer I use in Vim, a very short introduction to the most important x86 instructions, and here benchmarks of what you can try. Then going on with the benchmark, getting to peak flop without SIMD at this point still, and all the necessary information about how to interpret that. Why are those numbers the way they are, with links to the tables that document all these performance characteristics. Here's getting your hand dirty with SIMD itself. Basically what I life hacked, you can do this yourself and implement simple linear search. You can implement the for each that I showed the benchmark in a much simpler, less general way. You can try to generalize that. And then you can do more benchmark. Hit the peak flop and then linear search using SIMD. Compare that. We will see that glibc actually vectorizes this, but you can go faster than that. glibc uses an ifunc, so at runtime it has to dispatch, so it's always like a virtual function call. And since you are using SIMD directly, you don't have that overhead, and it's going to go faster. Here is a boilerplate with some strings, and you can get going right away. If you need more, you can do more and go up to interesting pictures. I expect you're not going to do this. But there are some solutions, at least here, so you can look at this. And also, when you clone this, there's another branch with results. So when you start with this, the main branch is like mostly empty. But you can also go to the other branch and look for inspiration, which is mostly, I think, what I put in here.